Hi guys, Dr. J here, and in this video we're going to derive the gravitational potential from a spherical shell, and that's going to set up the machinery that we need to be able to solve for the gravity potential of, for example, a spherical Earth later. So we're going to start out by just defining the geometry. We have a spherical shell centered at the origin with a very small thickness. The total mass of that shell is mass m. And the density of the shell, the surface mass density, is going to be just the total surface area of the sphere with radius a divided into the total mass. So mass divided by area, in this case, that'll be the surface mass density. The sphere does have a radius of a, and we can imagine a distance from a point on the sphere. So some point here is going to be at a distance s from this point outside the sphere up here at point P. And then the distance along this axis is going to be r. So just setting up the geometry of the problem. By law of cosines, we can relate all of these things together. So s squared is r squared plus a squared plus, minus 2r cosine theta. So law of cosines allows us to relate those things together. The potential of the shell is going to be negative g integral over the shell of sigma ds over s. Vg at the points P, so this is at the location, this is now not the distance, but just at the location P, which I guess actually is a distance r from the origin. Right, so we're going to integrate over the shell. The distance between that little piece of mass, that little increment of the sphere, and the point is going to be s, so that's where our distance comes in there. And then our density is going to be sigma, that's our density, surface density. And then we have our surface integral increment. So we're integrating over the area of the shell. All right, so I'm going to take this expression and I'm going to rewrite it over here so I have some space. And I'm going to kind of do a change of integral from, instead of integrating over the whole shell, I'll integrate in the out of plane direction, and then I'll integrate in the in plane direction. So the part of the integral, which is going to be the out of plane integral, that's going to be a function of the angle which is coming in and out of the plane, which we'll call that angle phi. There's no dependence, so we're going to imagine this little increment is going to be a ring around coming in and out of the board, and then we'll integrate with respect to theta, which is just going to be 0 to pi, top to bottom. And then we're going to have our 1 over s d theta. We're going to have a squared sine theta. So this integral is just going to become 2 pi. We'll end up with a 2 pi there. And a squared, that's a constant, that'll pull out. And so we'll end up with now we can do a change of variables formula. If we differentiate this with respect to s, we differentiate both sides of this, then we'll get a relationship between ds and d theta. So if we differentiate, we get that relationship. That'll be s ds is equal to ra sine theta d theta. Sorry, I ran out of space there. S ds is equal to r times a times sine theta d theta. So then we can get our sine theta d theta in terms of s and ds. We can plug that in here, and that is going to basically turn this integral. It's now going to be an integral from minus r minus a to r plus a of ds over r. So 1 over r times ds. 1 over r is a constant with respect to s, so that pulls out, and we'll just end up with r plus a minus r minus a, and this is actually going to be absolute value. So let me erase and write down our final formula. So the gravitational potential at point P from the mass in this spherical shell is going to equal 1 over r term. There's an a over r term here. We have our density term, g, r plus a minus r minus a. So we see our 1 over r term as we expect for the potential. We see the density times an area. So this is an area, or this is a length scale. This is a length scale. That's going to be an area. So density times that area, that's going to be related to that mass of that spherical shell. And so we can actually do this calculation for a point which is outside of the shell or a point which is inside the shell. So if we're outside the shell, then r is greater than a. So absolute value of r is just r minus. So absolute value of r minus a is just r minus a. So then we get r minus r plus a minus minus a. So we get this whole thing is equal to 2 times a if we are outside of the shell. So if we're outside of the shell where r is greater than a. So in that case, this becomes 2a, this becomes 2a squared. We end up with 4 times pi times a squared times sigma. And what did we say that was? We said that that was the mass, m. 4 pi squared, 4 pi times a squared times sigma, right? So that's the total mass of the spherical shell. So then this whole thing simplifies down. If we are in the case r greater than a, we get Vg is equal to negative g times m over r. Well, g times m over r. This should look familiar. This is our normal gravitational potential for a point mass with mass m. Pretty interesting. So if we're outside the shell, all of the material in the shell behaves as if it's a point mass located at the origin. That's a really important point here for gravity. So if we're spherically symmetric, if we're symmetric in respect to the angles, then all the mass, the gravitational potential from this shell is going to be just a function of distance. It's only a function of distance from the origin, which is the center of the shell. This is the case if r is greater than a. What about r less than a? What if the point P is actually in here, somewhere inside this shell? Let's take a look. So we have our potential here written out. Now r is going to be less than a, so that means that this value is going to be like a minus r. So we're going to have r plus a minus r. So then a's are going to cancel out. We're going to end up with this whole thing equaling 2r. This is going to be for r greater than a. This is going to be for a greater than r, right? Hope you're following. So this case is the case where the point P is outside. This case is the case where the point P is inside the spherical shell. So for inside the shell, we end up with a 2r. And now we end up with an r canceling out. We end up with 4 pi sigma a. R's cancel out each other and g. So if we have case r is less than a, we end up with Vg is equal to negative g. And we're going to throw in an a here so that we can still write this in terms of mass. Potential inside the shell. Any point inside the shell is going to depend on gravitational constant times the total mass of the shell times the radius of the shell. Gravity potential from this shell, if you're inside the shell, is exactly constant. It does not depend on where you are inside the shell. So if your point is near the edge, if your point is exactly at the center, if it's anywhere along this line, and this is going to be generally true no matter where the point is inside the shell, the gravity potential is a constant. And that means, by the way, that the gravity field is 0 inside the shell. So 0 field inside the shell. That is really interesting. So for any spherically symmetric density, we can decompose the body into shells, and the gravity potential inside that shell is going to be constant. We can calculate what that is. gravity potential outside the shell is just going to be our normal gravity potential, 1 over r. And that's going to be true for any spherically symmetric shell. Now, that's pretty crazy. Like, if you think about it, anywhere inside this spherical shell has exactly the same gravity potential. Pretty interesting. And that's going to have some really important corollaries. One of the corollaries that this is going to have is that if we can model our body as a spherically symmetric body, for example, a layered sphere like the Earth. So the Earth has inner core, outer core, mantle, crust. If we can model a body as a spherically symmetric body, we can decompose that body into shells, and then this applies to each one of those shells. And all the shells, if we're outside of the sphere, behave as if the mass is all concentrated at the center of the shell. So all the shells will act like that. And that means that all the mass, if you're outside of a solid sphere, all the mass is going to behave as if that mass is concentrated at a point at the center of the sphere. And so you're just going to end up with our normal gravity equations. If you're inside the shell, then we'll need to calculate what that gravity is, but the gravity potential is going to be constant from each individual shell. And so as you can imagine, we're just going to add up the contributions from all the shells which are inside, all the shells which are outside of where the point is, any point inside the Earth, and then use our other formula for all the shells which are outside, which will again behave as if they're all concentrated at the center of that spherically symmetric body. So the external gravitational field of any body is completely determined by its total mass and its multipole moments. That's Newton's third law, basically. So different density distributions that share the same multipole expansion cannot be distinguished by external measurements. That's the problem of our non-uniqueness, right? So this spherical shell is going to have the same exact gravity signal as a point mass located at exactly the center, exactly the origin, with having the same mass. And every other shell of every other size, which has the same total mass and is centered at the origin, is going to produce the exact same gravity potential at a point which is outside all of those spheres. That is the non-uniqueness problem. The non-uniqueness problem for gravity is not based on the noise in the data or not getting good enough measurements. It's based on the inherent behavior, this inherent fact that we can represent this spherical symmetry results in a gravity potential which is the same as a point mass at the center. All right, so that's all we're going to do in this video, and in the next video we'll go into some more details and some more implications of what this means.